Welcome back to Math 103. This is video number 15 on growth and finance. Recall from last time the compound interest formula. Future value equals present value times 1 plus interest rate to the nth power, where FV, future value, is what a sum of money or a population, whatever quantity we're talking about, will grow into. Present value is what it is now, where it starts out. I, the interest rate, is not necessarily the annual interest rate. It could be the monthly interest rate, or it could be the weekly interest rate. We saw that there is such a thing as more frequent compounding. So we adjust the given annual interest rate. It's typically given to us as an annual rate. We adjust it to make it the interest rate per compounding period, and of course in decimal form. And however many compounding periods there are, that's n. That's the exponent. Right? So we could raise the weekly growth factor to the number of weeks that compounding takes place, or we could raise 1 plus I, the monthly growth factor, to the number of months that compounding occurs. The crucial thing to understand is that this formula is just a summary of the same reasoning process we've been using from the very beginning of this topic. We're repeatedly applying a certain growth factor, namely 1 plus I, a certain number of times, namely n. Right? So PV gets multiplied by 1 plus I n separate times. Let's apply the formula to the following example. Suppose that you need to take out a loan today, and you anticipate being able to pay back $30,000 10 years from now. So you know how much you can afford to pay back. You don't know how much you're borrowing today. That's the question. If the annual interest rate is 9%, but that 9% is being compounded semi-annually, twice per year, we can ask, how much can you afford to borrow now? So we set up the compound interest formula FV equals PV times 1 plus I to the nth power, and we substitute in those values we do know and solve for the one that we don't know. Okay, the one we don't know is PV. We're asked, how much can you afford to borrow now? What is the present value of this financial transaction? This amount of money, PV, that we're trying to find, will grow into $30,000. So FV is $30,000. N is the number of times compounding will occur, and I is going to be the interest rate of this semi-annual compounding. So the interest rate, I, in decimal form, is not 0.09, but rather 0.09 divided by 2. Because in each compounding period, of which there are 2 every year, it's half a year's worth of interest that is being compounded. So each half year, the debt is multiplied by 1 plus 0.09 over 2. Now, how many times does this original debt grow by the semi-annual growth factor? In other words, how many half years are there in which PV is multiplied by that growth factor? Well, over the course of 10 years of being in debt, there are 20 separate growths by this growth factor. So n equals 20. Now that we've plugged in all known values in our formula, and the only unknown is our PV that we're solving for, it's just a matter of algebra from this point until the end. We have $30,000 equals PV times 1 plus 0.045 to the 20th. 1.045 is the semi-annual growth factor, and 1.045 to the 20th is the overall 10-year growth factor. That overall 10-year growth factor computes to 2.411714, and when we divide both sides by that number, we find that the amount we can borrow today equals $12,439.29. In other words, we get to borrow $12,439.29 today for the privilege of getting to pay back $30,000 10 years from now. Moral of the story, avoid debt if you can. Our discussion of more frequent compounding brings us to the important distinction between APR and APY, annual percentage rate and annual percentage yield. So to understand this, let's recall our example of a bank account with a 4.5% annual percentage rate. That is, 4.5% is the stated year's worth of interest, but we are told that bank compounds that 4.5% annual interest monthly. Let's call this bank Bank A. What is actually happening at Bank A? Bank A multiplies your account balance 12 separate times during the year. It multiplies your account balance by the 1 month growth factor we computed earlier of 1.00375. The effect of this over an entire year, that is, the effect of 12 separate multiplications by 1.00375, is equivalent to 1 multiplication by 1.04594. That is, the yearly growth factor, the 1 year growth factor, is 1 plus this 0.04594, which means that the effect of this monthly compounding is that the overall 1 year growth factor is greater than what it would have been if there had been no compounding at all. Just for the sake of our narrative, suppose that there's another bank across the street, Bank B. Bank B doesn't bother with monthly compounding, they just do annual compounding. But Bank B offers a higher annual interest rate. Their annual interest rate is 4.594%. Now, at either bank, your $3,000 investment will grow over the course of a full year into $3,000 times 1.00375 to the 12, which is the same as 3,000 times 1.04594. This growth factor is the overall 1 year growth factor at Bank A, but it's also the 1 year growth factor at Bank B. Either way, your $3,000 invested will grow over 1 year into $3,137.82. Your money will have exactly the same actual performance in Bank B as it does in Bank A. So we say that both banks have an APY, an annual percentage yield, of 4.594%. Please go on to the next video.